clearly separate consensus findings from working hypotheses where the data remain tentative. Discovery and early tracking. Atlas was discovered on July 1 by the NASA-funded Atlas survey. It was discovered using their telescope at Rio Ortudo in Chile, and it was first detected as a speck of light moving relative to background stars. That small flicker, barely distinguishable from the deep field of stars, marked the beginning of what would become one of the most studied and debated interstellar visitors in modern astronomy. The initial sighting quickly attracted attention, not only because of its faint movement but because its orbital characteristics hinted at something extraordinary. We will also focus on the specific measurements driving debate today and why the October 2025 close pass of Atlas by Mars is a critical chance to resolve them. In this video, we will walk step by step through the actual observations, including spectra, imaging, and brightness changes. We will look at how each either fits or challenges the comet model. By the end, you will be able to judge which claims are settled science and which remain open questions. To start, it helps to recall what astronomers thought interstellar visitors would look like and how that picture has already shifted. What interstellar visitors should look like. When astronomers first asked what a visitor from beyond the solar system would look like, the most common expectation was simple. A comet, a small frozen body entering our system, would warm up, release gas and dust, and form the characteristic coma and tail. That picture guided early searches and shaped predictions long before the first confirmed interstellar objects appeared. This classic image of a cometary interloper icy nucleus wrapped in outgassing jets, glowing coma, and a tail streaming in the solar wind dominated thinking for decades. But then a mystery interstellar object was spotted by astronomers last week. It could be the oldest comet ever seen. The discoveries of 1I Oumuamua, and 2I Borisov, quickly complicated those expectations. Instead of offering a clear pattern, they showed contrasting behaviors. One strange and unfamiliar, the other much like a comet we had seen many times before. By the time a third object, 3I Atlas, was detected, astronomers were already prepared for surprises, but its details still demanded closer study. The story begins in 2017 with the detection of 1I Oumuamua. Lessons from Oumuamua and Borisov. It followed a hyperbolic orbit, which means its trajectory was open-ended and too fast to be bound by the Sun's gravity. The consensus view here is solid. Oumuamua came from interstellar space. What surprised astronomers was everything else. Photometry, or the measurement of changes in brightness as the object rotated, suggested an unusually elongated shape. Some estimates placed its length-to-width ratio at 10:1, though this figure depends on models of its spin and surface properties. Along with its unusual appearance, Oumuamua showed a small but measurable non-gravitational acceleration. The consensus explanation has been that outgassing could produce such a push, but telescopes detected no visible jets or coma. Alternative hypotheses have been suggested, such as unusual materials on the surface, but these remain matters of debate rather than confirmed properties. The absence of an observable coma placed Oumuamua outside both main categories, comets and asteroids, at least by current definitions. What scientists could agree on was that standard comet models did not apply here. While details about its composition and dynamics remain uncertain, the object expanded the range of possibilities and highlighted the need for refined theories of how interstellar debris might appear. Just 2 years later, 2I Borisov provided a stark contrast. Discovered in late 2019, Borisov behaved like a familiar comet. It displayed a distinct coma, dust and ion tails, and spectral signatures of common molecules such as water and carbon monoxide. In plain terms, it looked almost exactly how astronomers expected an incoming icy body would look under solar heating. The consensus is clear: Boris strongly resembled solar system comets. And this set up a working hypothesis that interstellar objects could belong to a wide spectrum, from the unusual case of Oumuamua to bodies that behaved almost conventionally. This mixture of data set the stage for 3I Atlas. Atlas, a different kind of visitor. When it was first spotted, observers saw a clear coma almost immediately, which suggested a link to Borisov, but early measurements revealed important differences. Its coma showed unexpected chemical traits and dust structures. The light signatures did not align with those of standard comets, and its spectrum hinted at unusual compositions. For the scientific community, this was more than a curiosity. With only 3 confirmed interstellar objects, each new piece of data reshaped the framework astronomers used to classify them. Another factor makes ATLAS distinctive. Most interstellar objects that we have modeled would slice across the plane of the solar system at a steep angle, barely sticking around for extended viewing. ATLAS follows a path close to the ecliptic, less than 5 degrees off the plane in which most planets orbit. Because ATLAS's path lies close to the planet's orbital plane, more spacecraft and ground telescopes can observe it for longer. This increases the range and resolution of data we can collect, giving us a chance to track its evolution far better than with either Oumuamua or Borisov. Whether this near-perfect alignment is a coincidence or part of a wider pattern remains an open question, but its practical value for observers is undeniable. These circumstances highlight why astronomers are so invested in studying ATLAS before, during, and after its planetary encounters. Is it more active than Borisov, echoing some of its behaviors with higher energy release? Could it conceal similarities to Oumuamua under its dust and gas sheath, or is it pointing to an entirely new classification of small interstellar bodies? The consensus so far is that it does not fit neatly into either earlier case. Every additional feature that sets it apart forces a re-evaluation of what counts as typical. That leads directly to the most immediate puzzle. The first detailed measurements of ATLAS's light and chemistry are already revealing patterns that do not match expectations. Its appearance is shifting in both color and spectral signature, leaving astronomers to ask what hidden reactions are taking place in its coma as it approaches the inner solar system. 3I ATLAS chemistry and color do not add up. What has drawn the most attention in recent months is not ATLAS's orbit, but its chemistry and changing color. Each new spectrum has turned up data that stand apart from the normal sequence seen in solar system comets. Instead of following the familiar pattern of water-dominated outgassing, ATLAS presents a chemical balance that resists easy explanation. The consensus measurement reported in early spectra is that co-emission was stronger than HO, around roughly $3 Australian from the Sun. In most comets studied under similar